Hello and welcome to the pre-lab video for our Alka Seltzer analysis experiment, part of the York College of Pennsylvania General Chemistry 2 sequence this semester. So briefly, let's go through the goal of today's experiment and get right into some of the important details that are going to help you achieve that goal. We want to determine through the work of today's lab the amount, and that could be quantified several ways, but we're going to do it in terms of a mass percentage of the active ingredient present in an Alka Seltzer tablet. We can do this for any antacid, to be honest. We just happen to choose Alka Seltzer as our antacid for today. Now, the way we're going to accomplish that is through the use of gas laws and stoichiometry. The two primary gas laws that you'll need to invoke in your calculations are going to be the ideal gas law, PV equals nRT, and Dalton's law of partial pressures, stating that the sum of individual partial pressures of a group of gases will equal the total pressure of that mixture. You'll be conducting a reaction between an Alka Seltzer tablet whose active ingredient is sodium bicarbonate, or sodium hydrogen carbonate, with hydrochloric acid. In the aqueous form, these sodium bicarbonate molecules are mobilized. In the solid tablet form, they're not mobile, so therefore they can't yet react. But in the aqueous form, once they're dissolved into water, they're free to move around the solution. And when they bump into or interact with HCl molecules, also in solution, we get a reaction that produces water, salt, sodium chloride, and carbon dioxide gas. And it's that feature, the production of carbon dioxide gas, that's going to allow us to work backwards to determine how much sodium bicarbonate is produced. So the experimental objective will be to collect your CO2 and determine how much is produced during your reaction. Because it's related to sodium bicarbonate in this reaction, when you know the amount of carbon dioxide produced, in essence you know the amount of sodium bicarbonate that was used. That mass, though, will not be the entire mass that you add into your experimental setup. So you'll need to take that mass divided by the total to come up with the mass percent that I was referring to. Let me show you the experimental setup first before going through some of the analysis that we'll be doing as part of the work. So I'll pull in a setup that we have ready to go here. Okay. We're going to need a chamber for our reaction to occur. That's just going to be an Erlenmeyer flask. And since it's producing a gas, we want to transfer that gas into an area where we can collect it. We will collect that gas in a gas buret. It's a tall, looks like a tall test tube or long test tube. It really is very similar to the buret that you would use in an acid-base titration, except that there's no stopcock at the bottom end. It's simply closed off. Make sure you pay attention. 0 is the closed end, and it reads downward from there, since you would use this in its inverted fashion. To get the gas out of the chamber into the tube, we use this little transfer tube, and so you're going to have to get your hands wet as part of today's lab. The liquid, not right now as part of the pre-lab, but the liquid, when you're working with it, will have some acid in it. So if you have really sensitive skin, please be careful, or maybe ask your lab partner to do it. I'll demonstrate a quick way to do this. I'm going to slide my tube up so that its bottom is just below the water level. And then I'm going to quickly try to put my finger on the tip, down in, and slide it right up into the gas buret. And then I can re-lower the gas buret that way. Okay. And then I would have to dry off my hands. Wash them off because you have been putting them into an acidified environment. So it'd be best if you washed your hands. In the reaction chamber, you'll place some hydrochloric acid, and then you will prepare your samples of sodium bicarbonate or Alka Seltzer in a small gel capsule that you can add into the chamber and then quickly close it off. You'll want to agitate the chamber. It's really easy if you just loosen the clamp a little bit, and then you can shake it, rock it back and forth gently to help dissolve the gel capsule. We need that gel capsule because as soon as the Alka Seltzer hits the acid, it will start to react and produce the gas. And if we just tried to pour it in through the top, we would lose some of our gas before we could put the enclosure back into the flask, I should say. Once your reaction is completed, and you can't see it probably on the video, you'll have collected a sample of gas inside this tube. We need to know how much gas. So you'd think maybe it's as obvious as reading the level of the gas right now. But unfortunately, the gas pressure inside this tube and outside of it right now are not equal. This is a lot like a manometer, which we've talked about in class. You could think of it as a seesaw again. And clearly the water levels show us that the pressure inside is less than the pressure outside of our burette. So we need to equalize them. If you're lucky, you'll have produced enough gas that you could just slide your burette up and down until the level of gas inside and outside are equal. Now, as you're changing the pressure of the gas inside, you're also going to be changing its volume because of Boyle's law, pressure and volume being inversely related. So the volume I'm reading right now on my burette is exactly 33.00 milliliters. Let's watch what happens as I move my burette. So again, I'm going to have to put my hands in. First, I'm pulling out the tube, and then I simply push my finger on the bottom, and I have a tall graduated cylinder prepared that I can get my finger down in below, and as soon as my finger's below, I can take my hand off, and now I can move this up and down freely. So I lower this until the levels are equal. Now I'm reading only 32.24 milliliters. Again, notice my use of the scale. I've read 2 decimal places. The tenths are marked. I should be guessing at the hundredths place. We should always be properly reading our instruments. So the volume decreased as we increased effectively the pressure of the gas inside the tube. So pay attention to those numbers. It's kind of a neat effect to observe. But only when the level is equal inside and outside can you read the volume of gas in your burette. Okay. So that's in short how you'll collect your sample today. Once you have your sample collected, you need to know how many moles of carbon dioxide are produced. So you'll find the moles from the ideal gas law. But all of the gas in that tube is not carbon dioxide, as it turns out. Some of it is water vapor. Anytime we collect gases over top of water, some of the water also evaporates, contributing a small amount of pressure. So the pressure inside my burette, which was equal to the pressure of the atmosphere, so I'll read that from the barometer in the laboratory, that will be my total pressure. That comes from 2 gases, carbon dioxide and water vapor. Water vapor's value is a constant that I can look up online. There is a great resource available from the General Chemistry Laboratory site. You can find a link to a very accurate listing of water vapor pressure values at different temperatures. I would simply subtract that to then give me the pressure of the carbon dioxide that was produced. That pressure would be used in the ideal gas law, the volume, and the temperature, which is the temperature of our liquid water as well, to give me the moles of carbon dioxide. Once I know the moles of carbon dioxide, I'll use stoichiometry. For every mole of carbon dioxide, I used 1 mole of sodium bicarbonate. So that's a 1-to-1 calculation. And then using the molar mass of sodium bicarbonate, I will calculate how many grams of sodium bicarbonate were in my sample. So to calculate the mass percent then, I'll take the actual grams or mass of NaHCO3 that I calculated divided by the sample mass. How much was actually in my little gel capsule that you'll have at the start of the experiment. All of this is not sodium bicarbonate. What you calculated via your stoichiometry will be the amount of sodium bicarbonate. So it's the mass of bicarbonate divided by the total mass times by 100 that then gives you the mass percentage. Okay? You'll do the experiment 3 times, get an average of this, and then you'll be able to scale up from your little sample to how much sodium bicarbonate should be in an entire tablet of Alka Seltzer, and you can compare that to the value listed on the box. So be sure to read the box of Alka Seltzer because it has to, by law, define or indicate how much of its active ingredient is present. When you're done with all your calculations today, you'll be writing your first formal, complete, or full lab report of the semester. So let me take a moment to just briefly remind you of some of the components of that lab report. It should begin with an introduction and purpose statement. Identify the goal of your experiment, but also provide some insight as to how you will accomplish that goal. In pretty simple language, you can do that for this experiment. We've already gone over the goal, and we're using gas law and stoichiometry concepts to analyze that Alka Seltzer sodium bicarbonate content. So that's, in a nutshell, your intro and procedure for today. If you wanted to provide some extra information about acids in general, that's always appreciated and great to show that you've gone that extra mile to learn a little bit, provide some background on your topic. You'll want to give a brief summary of your procedure. You should not state word for word the procedure from your laboratory manual. That is not what's needed in a lab report. A lab report should summarize the procedure. Try to avoid giving exact numbers in your procedure section as well. You don't need to say that sample 1 weighed out as 0.227 grams, for example. You would indicate we weighed out 3 samples of approximately 0.2 to 0.25 grams. It's a much better way to approach the procedure. Okay? And give the important highlights of your experimental process. Data analysis and results. This is where you'll use the data template available in the usual fact data location to present first the raw data that you've collected, values for temperature, volume of gas, atmospheric pressure of the room, any experimental number that you collected in the lab, okay, will be presented in table format. Then you'll show the analysis, the calculations, and we ask that you show an example, or first show the formula, I should say, and then show an example substituting one of your data points, say your trial 1 value. Finally, give a table or summary of all of your results. You're showing one set of calculations, perhaps for trial 1, but we'd like to see the answer or result from all 3 of your calculations, and then any averages or percent errors as appropriate. And finally, your report should wrap up with a discussion. Discussion. What do you think? Was this a successful outcome? Is this a good way to analyze the sodium bicarbonate content? Feel free to pass judgment, so to speak, or provide an opinion on how the experiment went. Yes, you do need to think about what went right or what perhaps went wrong with the experiment. This is a very important component of any scientific work. The ability to be critical first of yourself and your findings before someone else has the opportunity to do it. If I was publishing a paper on my research, I would certainly need to stop and think, about these considerations. Was my experiment well designed? Were there any systematic errors in my setup? Were there any random errors that may have contributed to my outcome? This is where you can address those issues. We also ask you to address 2 questions in the discussion section about why citric acid is present in the Alka Seltzer tablet. Citric acid is an acid. It should react with sodium bicarbonate, just as hydrochloric acid does. The reason it doesn't, I referred to it earlier. It's the mobility. We need mobility of our ions to actually mix and mingle, so to speak, before they can react, complete this reaction. Why do we dissolve a Alka Seltzer tablet in our setup before we begin? This relates to the issue of intermolecular forces, which we've been addressing in lecture in chapter 11. Carbon dioxide, while it is a nonpolar substance, does dissolve to some extent in water. If we did not pre-saturate our water through which our gas is traveling, as it traveled up into our burette that I showed you earlier, some of it would actually get dissolved into the water. That would decrease the volume that we collect in our burette because some of it has disappeared into the water itself. So that's an important step to take into account. All right, thanks for your patience. Let me go through the pre-lab questions briefly, although these should be quite easy since we've covered gas laws thoroughly this semester already. So your first pre-lab question asks you to use the, or you need to use the ideal gas law to solve. But given that it's giving you the mass of a carbon dioxide sample, you could either first solve for moles, okay, or convert that mass to moles, or you could use the substitution that moles is little m mass divided by capital M RT. So we can manipulate this to solve for the volume. It would be little m mass RT over the pressure and molar mass. Make sure you convert your units, that you use the grams of the carbon dioxide, not milligrams, that you use the correct unit set for R, 0.08206 atmosphere liters per mole Kelvin, that you convert your temperature to Kelvin, and that your pressure is converted to atmospheres. When you're all said and done, you should have an answer of 0.324 liters. So make sure you show your work. The second question says we have a gas collected in a burette, and we're given a volume and a pressure, and then we reduce the volume, much like I demonstrated with our gas burette. So we're looking at just the relationship between pressure and volume. Temperature and amount are being held constant. So this is Boyle's law, and we can solve for the new pressure of our gas simply by dividing V2 under the P1, V1. Here the two volumes match up in units, so you should have no problem substituting and arriving at a pressure of 946 torr. No need to convert to atmospheres in that case. And our last question is also an ideal gas law question. Say we've collected an unknown gas and we want to identify that gas. One of the important properties would be its molar mass. So I can begin with this version of the ideal gas law for question 3 and solve for molar mass. So that would leave me with little m times RT still. So the m over there and the PV into the denominator. Again, make sure your units match up. You have grams for mass. R is 0.8206 atmosphere liter per mole Kelvin. Temperature in Kelvin. Convert the pressure to atmospheres and the volume from milliliters to liters. You'll get a molar mass of 71.0 grams per mole for the third problem. So that should address the pre-lab questions. Again, make sure you show your work and be prepared to hand those in as part of your lab preparations for this coming week. I wish you good luck in analyzing the Alka Seltzer content, the active ingredient content of Alka Seltzer tablet, and I hope you'll enjoy the experiment.